factoring polynomials. Should be I think it's the first page on that yellow packet that you're going to get handed today. It seems kind of thick, and don't worry, we'll chip away at it these next couple of days. And the beginning of it is just to take, we saw a little bit of this when we were doing our other review, but now I want to make it a little more formalized so you can see more examples of it. This first one where the lead coefficient here is 1 in front of the p squared. These are kind of like the easy type, the one that you probably remember the most because the factors of 20, this probably comes to mind, that add to the middle term 9. The 5 and 4 are factors of 20 and they add to 9. That allows us to factor this as p plus 5 times p plus 4. Does that sound kind of familiar? It's the easier one. Just the factors of that constant term that add to the middle term, that works anytime the coefficient on the lead p squared is just 1. So it's kind of the easy case. Keep an eye out for those. So number 7 kind of looks like a candidate because it has a lead coefficient of 1. And we may see if we can find factors of -6 that add to -5. And if we do, it seems like you'd think -2 and then 3, those multiply to make -6, but they actually don't add to -5, so be careful. You probably want to do -6 and 1 instead. So don't jump to quick conclusions, make sure you're careful. So y minus 6y plus 1 is the factored form. We're just rewriting this, so factoring is a way of just writing it in a different form than maybe you had before. So then, if we skip over, I think the next couple also have coefficients of 1. Now there are times when you don't have whole number factors where it doesn't work out this way. And it's not that it's impossible to do any kind of factoring, but you might have to factor with decimals or fractions, and at that point we're going to say not factorable with whole numbers. See if I can find one. I think there is one around here somewhere that doesn't factor. It may not be on this page, so hang in there. We'll look at number 4. Other factors of 18 that add to 9. We can do 2 and 9, and we can do 3 and 6. Oh, sure enough, 3 and 6 work. So it's h plus 3 times h plus 6 is the factored form of that. Okay, so think of that as the nice factored form. Sometimes you don't get whole number factors, and sometimes we can say it's not factorable in the whole numbers. You might go for another technique. So here it is, number 3. This is the next level when there's a coefficient in front that is not 1. One thing is if you could factor that out, divide everything by 2. If these were all even numbers, I would actually factor it out and use maybe the easier method, but this one doesn't. So what you do is there's what I showed you guys in class the other day, and let's formalize that again. You want the factors of the lead term, 2t and 1t, and the factors of the constant term, the -5 and 1, or 1 and -5. But what you need is a combination where you take the pair of products in such a way that those product pairs add to the 9 in the middle. And the magic combination, I forgot to put the negative in there, is when you take 2t times 5 and then t times -1, those add up to a positive 19. And how you paired them helps you figure out where the groupings go. Those lead terms, the 2t and the t, they always end up being your lead they're in your binomials right in the front. So let me put those in there first. They always go 2t and t, so you can place those first. Whatever you paired 2t with actually cannot go in the same parenthesis with it. So it got paired with 5. So you want to put that plus 5 in the other parenthesis, and of course then the -1 goes in the first. That's factored. So let's check that out again. Let's see if we can find another that works just like that. Number 11. Hopefully this one's not one of the unfactorable ones in whole numbers, but I think it'll work. This one has more options. So number 11 has, you could do 9 and 1, or you could do 3 and 3, 3p and 3p. I'll try that first. And then here I do -4 and 2 maybe. And let's see what combinations might work. We could do -12 plus 6. But if you realize that ends up giving you the wrong, that's -6p. You could actually just switch those around. So I might go in there with my wee eraser and change it up, put the negative on the 2, and that makes it positive 12 with the 3 times 4. And a -6, that's a magic pair. That works. Since 3p and 3p they go first, and you'd usually say, since 3p was paired with 4, you'd want to put the 4 on the other side. Since they're both 3p, it's not particularly meaningful. But there you are. There's -2. It goes in the front. So that's the factoring method I use. Again, if you've got another, you just stick with it. Do your thing. I'm going to skip down to some of the other types that are a little bit different. So those are trinomials that we just factored. We're going to get into binomial territory, like in number 6, where there's 2 parts here. You're always looking for a common factor, greatest common factor to make your work easier. These are both even numbers, so you could start by factoring out a 2. Make that 18 minus 50 w squared. Maybe you thought, oh man, I can get more out of it than that. I can divide those both by 2. So you factor out another 2, making it 4 out front. So I could have factored out 4 from the beginning. I'm sure you saw that. But just reminding you, you can just keep dividing out common factors as long as you like. And this is pretty nice when you get to this spot. Because this, of course, 2 times 2 is our 4. We'll write that in a minute. But do you remember there's difference of squares happening in here? This is something you want to recognize. 2 perfect squares being subtracted. And we factor that in that ever special way. So this will be 4 stays 4. But the 9 minus 25w squared, we do the square root of each. So that's 3 and 5w. 3 and 5w. And what we do is we add them and subtract them. And that's our factor pairs. Yeah, you can Graham and Ethan in the background as we're doing this lesson. So hope you don't mind a little action hero action in the background. But there's our factoring of a binomial that happens to be perfect difference of squares. 14. Looks like you can factor 6 out, and then probably it can do the same thing. I want you to notice number 5 here. Don't you look, the numbering, by the way, is absolutely sensical. Hope you're enjoying it, but these are cut and pasted from various sources. But k squared plus 25 is not difference of squares. So, but one thing you could do with it actually is, this is just, might want to circle and say it's not difference of squares, because we're not doing a difference, we're not subtracting. But it doesn't mean we can't factor it. It actually is something I can show you if you're interested when we get to it later. This is not the difference of squares, but it is something you could do as imaginary difference of squares. You could actually get, this would be k plus 5i and k minus 5i. Do you remember that whole imaginary number business? It's going to come up when you do solving quadratic equations. When you have a square root of a negative number that involves I, square root of negative 1 is I, and there's properties to it. It's called an imaginary number, which is a terrible misnomer, but it is something that is actually very tangible. It's just a necessary part of factoring and quadratics and roots and zeros. It's a mathematical necessity. So we'll get to more of that as we go. These initial units, remember, are just to kind of give you a preview of things to come and kind of get your skills back in order. Okay, so I think we've done a little bit of each type of factoring, so I'm going to call it good and then get on to the next section where you guys are doing quadratic formula. And we're also going to do graphing quadratics, and it involves completing the square.